So let's talk about support vector machines. So these are machine learning model which uses boundary to separate between two classes. Here we can see in 2D space there are cluster of data points which belong to the red cluster and the blue cluster respectively. So here we need to find the optimal 2D boundary. So this straight solid line which can efficiently separate between these two data. So here in SVM, these classes here which belong to the class -1. Here it belongs to the class +1. Here this middle line is the 0 line. So this is the separation at separation point. It will belong to neither of these classes. That's why it's 0. And here, this line here, all the data points on this line will be +1, and the data points above this line will be positive values. And similarly here, we have this dotted line. Here at this line, the value will be corresponding to -1, and beyond this there will be negative values. So as you can see how we can find this dotted line. So it will be logical only to find the dotted lines. When we find them with the help of the closest points for these two classes which are closer to each other. In other words, where they are in the edge of these two clusters which are closer, because only then the separation line would be optimal. So only with these edge data points, so these are called support vectors because they are only used in finding the optimal boundary of separation hyperplane. So let's say there are yes, there are infinite number of or many number of lines, so here which separates these two data clusters. So let's say instead of this existing line of separation, I take this original line itself, or a line slightly above this dotted line which separates them as negative class. So here, if we have the data line of hyperplane separation as here, all the data points here in this side, they will be classified as blue because it is to the upward side, other side of the separation line. But in reality, we can see logically these data points are closer to this red cluster. So they must be logically classified as red, but it is classified as blue because of this inefficient separation which we got here. So that's why they must be right in the middle, or they must right in the middle of the classes for separation, so that they can be separated optimally. So these are found using the data points on the edge of the cluster or which are closer to each other. So these vectors on this edge are called as support vector. So here for separation, here in 2D space, we have a single dimension line as the hyperplane. Similarly, in case of a single dimension, which is a single number line, let's say this x-axis alone, we have the red data points and blue data points here. Here the separation would be just a dot. So in single dimension, dot is nothing but a 0 dimension. Similarly, in case of 3D, the separation would be a 2D plane. So similarly in 4D, it will be a 3-dimensional object of separation. And similarly, in n dimension, n, the separation would be a n minus 1 dimensional separator. So that's why we use a term called hyperplane. So hyperplane is nothing but the generalization of this boundary of separation. Or in case of here, we can see that it's a dot from a line to 3D and so on. So we cannot have a name for higher dimension. We cannot visualize it. That's why we generalize them, and we can call them as hyperplane, which is represented by this equation here. Here the value is 0, which is separated by this, which is represented by this equation here. Here W is the weight, which is normal in 2D place. It is a weight vector which is normal, which is perpendicular to the hyperplane. So W vector is the perpendicular to the hyperplane here. So here we can see they are here it is a vector. In higher dimension we can increase it more. So in case of 2D we have two inputs, so we have two weights. W is the weight, wx1 plus w x w2 x2 plus p equal to 0. Similarly, in 3 dimension, we have three of these terms, so we can expand this. So likewise, we saw in logistic regression, and W is the input vector and P is the bias term. So using this, we can represent this matrix form or this equation. We can represent any hyperplane here. So in this case, for 2D, it's just a line. So this corresponds to the line separating these two. And the goal here is to maximize the margin here. Margin is nothing but the distance between the two dotted lines or these two equations. So this below equation corresponds to this mathematical expression. At this point, the value will be -1 and beyond this it will be negative. Similarly here, this is the positive equation and this is the neutral equation. The goal here is to maximize this width so that we can find the efficient boundary which can separate these two data classes. So the efficient data boundary is only found when we have the maximum distance here, so we can get a clearer separation. As we saw in previous example, it won't work when we have the line here. That's why the line need to be like in the sweet right spot so that they can be separated easily. So that can be achieved only when we maximize this distance or when we maximize the margin. So we need to maximize the width. So our original condition, all this point below this must be negative, below this line must be data points must be negative. So this equation can be written as plus b is less than or equal to 1. So for the negative side of this graph, the data points must satisfy this equation so that they can be negative. Similarly for positive, they must satisfy this equation condition, that is they must be greater than or equal to 1, which is from this line and above. So this is the condition for the data point. So these two equations can be combined and be represented on this single equation. So here we introduce another term for AI, which is the output class itself. So here the class is 1. You'll have the same term, which is nothing but the positive condition. Similarly, if the output class is -1, this inequality will be reversed and we will get the negative condition. So this term is introduced just to simplify things mathematically and to get a better representation with just a single equation. So let's say quickly about hard margin and soft margin SVM. So here in this case, let's say there's a data point for the red class or the negative class, which is present here. So according to our intuition, we need to draw the line of separation from the closest points of these two classes, which should be like around here. The line of separation would be around here. So in this case, it doesn't make any good sense because here this point here would behave as blue, but due to some outlier data present here. So here this is not a viable solution for separation because all these data points near here would behave as blue according to our original separation which we assumed. So that's why we need to allow misclassifications. So misclassifications mean this is a misclassification when we have the line here, which is the optimal line. This would be misclassified as blue because here the data point is actually red, but just because we have the data points near the blue cluster, they would behave it as blue. So just to accommodate this error and to give the optimal line of separation so that we can separate the data points in the blue and red data on a global level, we need to accommodate this misclassification, which is nothing but a soft margin SVM. So if we don't allow any misclassification, so there is no misclassification here. That is when the data is completely linearly separable. That is, we can separate them with just a single line here in case of 2D. So in that case, we use hard margin SVM. So if we have outlier data and we need to accommodate those, we need to use soft margin SVM. So now let's see the mathematical part. Previously we saw that our objective is to maximize the width, which is these are two or the hyperplanes for either of these classes for as separation boundaries. So we need to find this width and maximize it. So we need to, in order to maximize this margin, we need to find what is the actual distance. So we need a numerical formula or notation to calculate the distance between these two hyperplanes. So that's what we're going to derive now. So let's say here we have the hyperplane, this line. The formula is this one, where we have the W, which is the weight vector, which is normal or perpendicular to the hyperplane itself. Previously we saw this notation. So here W transpose X is nothing but that represents the dot product between these two. That's why it's represented as transpose. So here we directly denote them as dot product. And B is the bias term, which is offset from the origin of this hyperplane, how far it's shifted from the origin of this hyperplane. So we have this equation here. Similarly, let's take two arbitrary points, x0 and xp. Here xp lies on the hyperplane itself, so it must satisfy this equation. That is, when we give the input here as xp, they must be satisfied. So we have the equation for xp here. Similarly, we have the point x0 here. So now for finding the distance or distance of separation of the margin in order to find the width, first we can find the distance from any point to the hyperplane itself. So here the any point is x0. So first let's vector for this x0 and xp. So this is the vector from x0 and this is the vector for xp. So now this green line is the distance which we need to find, which is the shortest distance from this point to the hyperplane. So this is what we need to find. Here we can see this, the shortest distance from this point to hyperplane is also perpendicular. So this is also parallel to the normal vector W. So this W is parallel to this shorter distance which we're gonna find. This is what we need to find. In order to find this, let's draw another vector from x0 to xp. So this vector here is the vector subtraction between x0 and xp. So this one can be represented as x0. I'll draw it in yellow. So that is x0 and xp, x0 minus xp. So from this, we can find the shortest distance between this point and hyperplane, which is the perpendicular distance. So how we can do that? So here, the t which we need to find here, we can say that as magnitude of the projection of this vector which we saw, the subtraction vector, on the normal vector w. Why? We can see the magnitude is nothing but a projection of a vector onto another vector. Here we have t. So this is the normal vector also, which can be represented as here. So if we have a torchlight here, which is the projection definition, like if we see the torchlight from this angle, you can see that this full distance would be confined, and we can see the actual length on this axis on the normal vector itself. So we can see the magnitude or the distance. So using this intuition of projection, we are using the projection formula in order to find this d distance. So we saw this in vector algebra. So here we can see the projection formula. Projection is nothing but uv by magnitude of v for projection of the vector u on vector v. So we have, how do we get this? So we saw it already. We have the dot product formula, which is nothing but magnitude of u and v cos theta. So in this right triangle, d is the adjacent side which we need to find here. Let's say this is theta and d is the adjacent side. Adjacent side is nothing but uh, u cos theta. So this is the projection which we need to find. So if we have the projection and take this to other side, we'll have magnitude of v on the denominator. So projection equal to uv by magnitude of v. That's how we get this formula. So projection here, it's d, which is nothing but the magnitude of u cos theta. So we have it here. Or on the other side, we can take this other, we can interpret this as unit vector, which is v. So here u is nothing but this one, x minus xp, and v is the vector here, which is the normal vector d, which the distance we need to calculate, or the in vector terms, this is the normal vector, which is the v. So here we can, using the projection formula, here we can substitute the value of u and v here. Similarly, for the denominator, we have v as w. So if we take this magnitude, we will get the distance. So here we can just multiply this inside. So here if we multiply for each term, we will have these two. So if we see the hyperplane formula for xp here, you can see that xp, dot product of w and xp, is nothing but minus p. If we take as I said is minus p, you can substitute this minus p here. So we have already another minus. So we have minus of minus b, which is plus b. So we'll have plus b from here to here, and that's how we get the distance formula. So why we do this? Because we need to represent everything in terms of this original hyperplane. So that's why we substitute that here. So using that, we get the distance formula for a point, from a point to the hyperplane here. So using this, we can find the margin, which we're gonna see next. So now that we found the formula for distance between a point and a hyperplane, let's come back to our original problem. We need to find the distance between the two separating hyperplanes. So this red represents negative values and this one blue line represents positive value. So middle we have the hyperplane where the value is equal to 0. So it is equidistant from these two. Our goal here is to find this distance and we have to maximize this. For that, we derived a formula before for d. So let's take an arbitrary point x0 on this hyperplane h1. And using the formula which we derived before, we have this one. Why do we have b dash instead of b? So we find the distance from this point to the hyperplane where the right hand side is -1. But in a formula which we derive, which requires the hyperplane equation to be 0 on the right side, so that's why for simplicity we can take this minus to this side. We can have b plus 1, and this whole b plus 1 term we assign it to a new variable called b dash. So that's why we get b dash here. So the next thing is here in this equation, wx plus p equal to 1. X naught must be satisfied in this hyperplane equation itself. We have it here. So we, instead of x, we substitute x naught. So we have dot product of w and x naught on one side. On the other side, we'll have 1 minus b. So now that we have these two equations, we can substitute them here. So b dash is nothing but p plus 1, and dot product of w and x naught is nothing but 1 minus p. So that's what we did here. Here we have the numerator term as the substituted terms. Here b and b will get cancelled, and you will have 2 in the numerator. So this is the final formula for the margin or the distance, for the distance between these two separating hyperplanes. This is d. Our goal is to maximize this function. Now we have a definite function in order to maximize them. So in order to maximize this term, we can put in the term that we need to minimize this denominator term, so that the numerator, the whole term will be more if the denominator is less. So this can be written as we have to minimize this term w. So we just not need to minimize it blindly. We also need to keep in mind that we have this constraint or restriction which we saw before, that the all data points must be satisfying these two equations, which we combine them and return a single equation, that uh, the data points must be negative on this side and positive on this side. So we have to minimize this with respect to these constraints. So this is our optimization problem. Now that we got our objective function, which is we have it here, which is we need to minimize this w in order to maximize the distance between the boundary. So this can be represented as half of this w square. So minimizing this is same as minimizing this whole function. So why do we write this half and square? Because for max simplicity purposes, so that when we differentiate, this 2 will come here and the 2 will get cancelled. So that's why we do this mathematical addition here to this. So we need to minimize this whole function. So for this, for normal minimization, we just do the partial derivative like in logistic regression. But now here we have another constraint, which is this one, like we saw before. So the original problem is now is minimization, which is optimization under a constraint. So to do this, we use the help of Lagrangian multipliers. So what is Lagrangian multipliers? So to optimize the normal optimization function under a condition, we have a new equation called Lagrangian equation, which accommodates both of this original function and the constraint equation by introducing a term called Lagrangian multipliers, which have the have any symbol. Here we have it as lambda. So these are Lagrangian multipliers. So let's see how we can derive it. We can see the intuition of it. So, as I said, the new function of Lagrangian function. Let's say we have an original function f of x. So this can be any function which we need to optimize. Here it is this one. And let's say we have another function g of x. So this is nothing but the constraint function. Here this is the constraint function, but for generalization, let's keep it as g of x. So for this optimization of f of x under the constraint g of x, we can write the Lagrangian equation as f of x plus lambda of g of x. So here the lambda represents the Lagrangian multiplier. So in this way we can solve the constraint optimization problem. So let's see the intuition behind it. Let's say this U curve is the optimization curve, convex function. We know it. So here the gradient descent. So in that we will change the hyperparameters. We will take a step-by-step approach in order to get to the global minima here. So this is our final point. This is our solution, our global minima. So this U curve is the function which we need to optimize, which is the f of x itself. So here, this is the point which we need to reach, which is the global minima. So imagine a ball which is rolled down from a hill. So we have a ball, we roll the ball along with this curve to reach this point. So this is our goal, but now it's not a normal optimization problem. We have another constraint, g of x. So let's say in this case, g of x is a line, vertical line like this. It's a vertical line like this. So it is an inequality. Let's say g of x has the values greater than 0. Let's say this line is where the 0 is present, just suppose, and greater than 0 means g of x greater than or equal to 0. Let's say something like this. So it takes all the values to the right side of this line, let's assume. So all the data points on the right side of the line, blue line, feasible region. So every data point here is the answer, which is the feasible solution for that inequality constraint alone. So the final answer must also be in the feasible region. So let's say we roll down the ball from there to here in order to reach the global minima, which is assumed to be here. But just because you have this inequality constraint, the ball stops rolling into this region. It will stop here when we roll down, because think of the inequality like a wall, vertical wall, which is like blocking the path of the ball. Because the only feasible solution is this side, so the ball cannot pass this side. So in contrast to the original optimal solution, when we have the inequality condition, this must be the solution with respect to the constraint. So this would be the minima instead of this one. So this is when we have no constraint, which is the unconstrained problem. So this is the new one. So this is what we need to find. So let's go to the formulation. So let's say here the ball is moving in this direction, which is opposite to the gradient of this optimization function. So gradient of this optimization function is nabla f of x. So here we have it as, so imagine it like a force which is exerted on this ball by this curve. So it will be in the opposite direction. So the force actually, it will be the negative of the gradient because it will be opposite direction. So this is the force on the ball and it's on this direction. On the similar hand, the wall will exert some force. That's why when the ball is rolled down, imagine this like a wall, the ball will stop here because at this point the gradient will be 0. That is, the slope will be 0. Originally at this point the slope will be 0 because this is the lowest point, but here the slope will be 0 because it's not because of the lowest point. It's because the constraint, which is the wall, exerts the amount of force which is equal and which is balancing out with this force exerted on this ball. So they will be just equal, but they will be in the opposite direction. That's why they will cancel out and we will reach the state of equilibrium or stationary. So this is what we need to find. When the ball is here, the force will be exerting on the ball in this direction and the ball will exert the force on this direction, the blue line. So the force which is exerted on the wall, which is this one, against the ball, which is the gradient of the, which is normal to this ball, which is represented by gradient of the constraint function. So this force will be equal to this force at this point, and they will be in the opposite direction. That's why they will cancel out and we will reach the equilibrium state. So when we put this mathematically, we will have the total force would be 0. So if we add the effect force or the effect of these two things for x, gradient of g of x would be 0. At this optimal point, they would be 0. In order to accommodate the magnitude differences in the force, so here the ball will roll in some force, some magnitude, and the force will be exerted by this wall in some magnitude. So the magnitude must be equal. That is, if here the force exerted, let's say, is 4 Newton, and similarly here it should be 4 Newton, but it should be in the opposite direction minus. That's why in order to accommodate the change in the magnitude, we can introduce a new multiplier lambda. So using this multiplier, we can actually change how we can actually accommodate the difference in the change in magnitude here. So here we can take this to the other side, this lambda uh, gradient of g of x, just snap out g of x, you'll have this one. So it says that the direction is opposite. Here we can see these forces are opposite because we have this negative sign, and the magnitudes are equal at this point because it is at equilibrium state, and this difference in the magnitude of the force is accommodated by this lambda. So that's how we can represent any optimization problem under a given constraint with help of the Lagrangian multipliers. So the star is just to denote the optimal solution. So what is lambda here? So lambda here tells us how strongly the wall pushes, which is the magnitude of the force. So if the wall here, if it is not even touching when we have the ball rolling down, so instead of the wall being here, if the ball is like on the other side, let's say like this one. So here the ball doesn't need to touch the wall because before even we can reach this point, we will reach the unconstrained minimum shear. So that's why in this case the value of lambda would be 0 because the ball isn't touching the wall. But if the ball rests on the wall, the lambda will be greater than 0, as we saw in the previous. So now let's move on to the next step. So here we have to assume the Lagrangian functions. So here our objective here is to find the optimal value of the lambda Lagrangian multiplier along with the optimal solution, which is represented by this. So this is what we need to find. So in order to assess the feasibility, like if we can find the optimal solution for a given Lagrangian function or not, we need to find the satisfaction of another set of conditions, which is called Karush Khun Tucker conditions or KKT conditions. So these are the 4 conditions. So using these conditions, we should check if the given equation and other metrics satisfy these, and after that we can proceed in solving them to get the optimal solution. So let's see the intuition behind these 4 conditions, which we already saw before with the previous example of the ball rolling down a wall. So here this would be the optimal minimum, which we need to find on unconstrained problem. So the first condition here is the stationarity, which says that the valley slope in addition to the wall's push must be equal to 0. Valley slope is this one. which is the nabla f of x star, which is the optimal solution. So at this point, we can find the optimal solution because the wall will stop here. Imagining this would be the feasible region of the blue function, which is the constraint function. So at optimal point, the ball will be stationary. It won't move because the added forces would be zero. So that we saw previously. So the next condition is the primal feasibility. So primal feasibility, because we need to find the feasibility of the constraint function itself. So this is the constraint function. So the optimal point, the constraint function must satisfy itself. So the solution cannot be on this side of the on this side of the constraint inequality. It must be itself be located on the feasible region of the constraint function, because that that's what we need to find, and that is what logical. So that in that way we can ensure that the solution has primal feasibility, that is, the ball must lie inside or on the wall and it's equal to zero. So we need to ensure this one. And the next rule is we have dual feasibility, which says that lambda has to be greater than or equal to zero here. So again, imagine what is lambda. Lambda is nothing but the magnitude of the force which is applied by the wall to push against the ball which is on here to keep this ball on equilibrium. So the magnitude of the force lambda, which is a push force, which can be only positive or zero. It can never be negative. So if it is negative, it will give the implication that the wall is pulling the ball towards, if it's having negative force, but that is not possible. The constraint here, the constraint function or the wall logic here only pushes the ball against the ball, uh, the ball against the wall. So that's why the lambda, which is the magnitude of the force, in this case we take the analogy of it. So it must be positive or zero. It ensures the dual feasibility. And similarly, we have the next rule, which is contemporary slackness. So what is contemporary slackness? Which is given by this equation. Lambda times g of x, when the optimal solution, x the optimal solution, must be equal to zero. So why do we have this? So it is present in order to accommodate two different cases of solution. So we have the case one, when the ball is not touching the wall. So instead of here, as we saw before, the if the wall is on the other side, this would be the feasible region, and before even the ball reaches the wall, it will reach the global minima directly here. So in this case, the ball is not even touching the wall. So here the g of x, this gradient function would be greater than zero. So here, which implies that the wall has no effect on pushing the ball because it's not even touching. The magnitude of the force exerted will be zero, so lambda will be zero. So in this case, lambda will be zero, so this whole equation will be zero. But on the other case, when we saw the line was here, there is some force which is exerting on the ball, so the lambda will be not zero, it will be a positive or equal to zero force, because it can never be negative with the dual feasibility. So if it's touching the wall in that particular moment, this would be zero. The gradient of the constraint function would be zero. So these two cases ensures the contemporary slackness condition of this Lagrangian equation. So only if all these four conditions are satisfied, we can find the optimal solution for the Lagrangian equation. Now let's see how we can apply the Lagrangian concepts and KKT conditions which we saw before to our problem of SVM. Here this is the function which we need to minimize, which is f of x, and subject to these constraints g of x. Here we had one on the right side, we just took it back to the left side for mathematical simplicity. So now that we have f of x and g of x, we need to build the Lagrangian function. So L, which is f of x plus lambda g of x. G is the constraint function. Here we can substitute f of x, which is half of w squared. And similarly, for g of x, we won't be having a single Lagrangian multiplier. Here we use alpha to denote the Lagrangian multiplier. For each data point, we'll have a set of Lagrangian multipliers. So the inequality, you'll have a set of inequality for different data because we have I term which represents the data number in the table, or let's say for second row, or to mention the second data, you'll be having y2 w dot product of x2 plus p minus 1 is greater than or equal to 0. This is point 2. Similarly, for point 3, we'll have this as 3 and 4 and so on. So similarly, we'll have more I Lagrangian multipliers for each. That's why we write alpha I and we do the summation in order to add them and consider them together. So here we have this condition. We just take this minus outside so that we can have minus here. So this would be the whole Lagrangian equation. Now that we have the Lagrangian equation, now we have to check for the conditions, KKT conditions. So how can we do it? First one is stationarity. That is, we need to prove that the partial derivative of the gradient with respect to partial derivative of the Lagrangian function with respect to w and with respect to b, each must be equated to 0. So in order to prove that, we can find the partial derivatives with respect to w and b. This equation we just expand it, we just multiply from this equation inside and expand the terms. So only if we prove that the gradients are 0, we can prove that the opposing forces on the curve which we saw is 0 at the equilibrium, which is imposed by calculating the gradients. So here with respect to w, in these two terms only we have w, we don't have any w in these two terms. So here that derivative of this one, 2 and 2 will go away and we will have just w. That's why the reason we take this as half of w square. So we have so that we can have w here. Similarly here, derivative of w is just the coefficient of this one. So we have the same thing here. So this, when equated to 0, if we take this to the other side, we'll have w is equal to this one. Similarly, when we partially derivate with respect to b, only this term has b, so rest every term will be cancelled. So here the b coefficient of the b is just the answer. So here we will have this one equal to 0, which is nothing but this summation is equal to 0. So now that we have these two equations, we can substitute them in our original equation. So here we have w square. So this w term we can substitute here, but we have to multiply it 2 times. So that's why we have 2 of these things here, and we have half. And this term would be 0 because of this equation. So this is 0. So this will go away completely. And this last term, we have it here. So here we can substitute the w. We can go on and substitute the w here. So W is nothing but this one, so we have it here directly. And we have the rest of the terms here, same as here. So notice that we use different notations like K and J, though we do the same multiplication. These notations are used just to show the product of vectors when while doing, so while doing dot products. So in order to differentiate the places where it's coming from before dot product, so let's say we have the dot product formula here, where we have a vector which is summation of a1 and a2. So when we do the dot product with itself, so what do we have here? We have a1 plus a2 multiplied by a1 plus a2. So if we multiply this both, we will have cross multiplication a1 plus a1 a2, and similarly we'll have the rest of the terms. But here, if we don't have the indices 1 and 2, it will be just like a plus a and a. It won't make any sense. So here this notation says that this part comes from this vector and this part comes from this vector, so that it makes our interpretation clean. That's why we use different variables here. So now that we did everything, so this is our substituted expanded equation. Now let's proceed to solve this. Let's simplify this equation further. Now we have this equation, so if we multiply every terms inside this, we will get this equation. You can just cross multiply, and here we have, if you notice, we have the same thing here and this term. So only difference is we have half here and we have -1 here. So half minus of something is nothing but minus half of this something, and this term we have it the same as it is here. So what we derived here called the dual optimization problem. So in starting in the Lagrangian equation, we had only the terms with constituting of the variables w and p and lambda. So here, in the dual optimization problem, we have the equation consisting of only the alpha, the Lagrangian multiplier, and we have the dot product of the input terms. So actually, we don't even need to find what the input are. We just need to find the dot product between them, which moves us to another topic called Kernel Trick, which we will see later, which makes our life easy. So we can see the importance of it later. So one of the goal here is to maximize this alpha and find the values of this alpha subject to these constraints. So this is from the derivation which we did before while doing the first KKT condition, and this is the dual feasibility condition, that is the alpha I must be greater than or equal to 0. So why do we need to maximize the alpha? Because if you go back to the U which we saw before, and let's say this is the separating constraint, the data points on this are just lying on the point here, which is stopped by this wall or constraint. It will be exerting a positive force on this direction. So the magnitude is nothing but alpha, as we saw before. So only at this point the value of alpha will be positive. So that's why we can maximize this, and we can find the data points which are actually on this junction, because on the all other points the alpha will be 0 because the wall will be exerting no force. So by finding this point, we can actually find that support vectors, because this is the last point where the uh, point will satisfy all these equations, and it will also satisfy the constraint, and it belongs to this class. Beyond this point, it is not classified as this class anymore. So this is the last point. So the last point is nothing but the support vectors. So the support vectors, if we draw a hyperplane, we can find the decision boundary. So that's why we need to maximize the alpha so that we can in turn find the support vectors respect to these constraints. Also, another advantage is this dual optimization problem. We can find it easily by computers with quadratic programming methods or quadratic um, optimization methods. So here we will find the set of alpha where it is actually positive and zero. So, but we care only about the alpha where it is positive, so that the wall exerts force. So, using this alpha value, we can for each data points we can go and find the data points which will actually have effect, which will actually have positive value of alpha, and we can ignore the alpha values data points where the alpha value is zero. It can only be positive or zero. So after calculating the support vector, next step is to consider construct the hyperplane for separation. So for constructing the hyperplane, we need to find the values of w and p for this equation, because to satisfy this equation, so w we calculated with this formula, which we also derived before previously while calculating the partial derivative with respect to w of the Lagrangian function. Next thing is b. This also we can find it with the input function which we used before. So here let's say the support vector is xk, and using this function, this equation, we can find the value of b, and we can eventually construct a separating hyperplane. So after constructing the hyperplane, the next step is finding the prediction, which is the decision function. So here we have the function, just the sign value of this equation. We can expand this with this one as we saw here. So the answer, after substituting and calculating with a new data point, so if our f of x is a negative value which is less than 0, it will be classified as negative class, -1 class. If it is positive value which is greater than or equal to 1, it will be classified as positive class, which is +1. So that's how the whole SVM works. Now let's see the intuition behind kernel trick. So now let's say we have some data points belonging to two classes on just one axis, x-axis. So we have the red class data, and let's say here we have a cluster of other red class data, and only in the middle we have the green cluster data. So in one dimension it's hard to use a point to separate these two data classes because they are on the either side. So that's why what we can do is we can change this into two dimensional. So for the y-axis we're just gonna have this x value squared, and for x-axis we're gonna have the same thing. So if we just square this, x-axis will be the same but the y-axis will be the squared. So it will be like here, and this point will be here, and this point will be here, and it will be like this. And similarly here, um, the let's assume the data points are like this, and for these 4 points the data points would be like this. So here if you just plot and see the values, you can actually find a line, a slim line, which we can use to separate between these two data class clusters. So here the diagram is a bit off, but you get the understanding of why we use different polynomial functions in order to find the optimal line of separations. Sometimes this might not be possible, and we need to use a cubic function instead of y equal to x square. We need to use sometimes x cube, uh, so that the optimal boundary might be found on that equation. So cubic means it will be like this. It will be curved upwards. So similarly, we can be able to find the optimal separating hyperplane by increasing dimensions. So This is what is kernel trick, that is transforming the original dimension into higher dimension space in order to find the relationship between them. So here we have the dual um, optimization formula. So here this said this dot product is used for kernel trick. So what is a dot product? It tells about the similarity between two vectors. It tells how the one vector moves in the direction of other vector. So this idea of this can be used to we can just replace this dot product with kernel functions like this polynomial function. So this is called as polynomial kernel. So here we can see it is in the form of a polynomial where d is the number of d is the dimension, and these two terms r and gamma here are just the scaling terms for the polynomial. Similarly, we have another kernel function called radial kernel. So this is a bit complex one than the polynomial kernel. So RBF radial kernel essentially measures the similarity between 2 points based on the Euclidean distance, which we usually find in vector algebra. So it creates a complex and non-linear decision boundary. Here we have a linear decision boundary, but there it's a non-linear decision boundary which can separate data when it's like in a spherical or spiral pattern, which cannot be represented just by graphs here. So this for non-linear functions. So what makes it possible and easy here? So here we don't need to like explicitly transform the data points to higher dimensions. So this dot products enables us to just find the relationship between two vectors or points in the space. So that's what dot product is. So by just calculating the relationship, we can replace this function with any function we want, and we can just find the relationship between data points in higher dimension without actually transforming them. So that's why the importance of the dot product here is crucial in this dual equation here, and this is called as kernel trick.